In the rapidly evolving landscape of human-centric cross-modal intelligence, motion-language retrieval stands as a foundational task, bridging the semantic gap between natural language and human motion. Its applications span from intuitive motion understanding and style transfer to controllable motion generation, making it a cornerstone of next-generation embodied AI systems. Yet, despite significant progress, most existing methods remain trapped in a global-centric paradigm. They align entire motion sequences with holistic textual descriptions. This approach, while effective at a high level, fails to capture the nuanced, fine-grained interactions between local motion segments, individual body joints, and specific text tokens. As a result, the model misses critical semantic details, such as the precise timing of a footstep, the coordinated swing of an arm, or the subtle shift in posture, that are essential for accurate, interpretable retrieval. To overcome this limitation, we introduce Pyramidal Shapley-Taylor (PST) learning, a novel framework inspired by how humans perceive motion, not as a monolithic sequence but through a hierarchical, multi-scale process. Human motion perception unfolds in three distinct stages. First, at the joint-wise level, we observe individual joint trajectories, how the left arm swings, how the root joint translates forward, how the right leg lifts. These low-level dynamics form the building blocks of motion. Second, at the segment-wise level, these joints are grouped into meaningful motion segments, like walking forward or turning left, where temporal synchronization and dynamic coherence emerge. Finally, at the holistic level, these segments are synthesized into a unified, coherent action, integrating localized kinematics with global semantics. This pyramidal process is not just cognitive, it's optimal. It allows us to reason from parts to whole, capturing both fine-grained detail and structural context. Our framework embodies this principle. We decompose human motion into temporal segments and spatial body joints. Then we train the model in a progressive, three-stage alignment process, joint-wise, segment-wise, and holistic. But how do we ensure the model learns meaningful correspondences, rather than superficial correlations? Enter Shapley-Taylor Interaction, STI. STI is a powerful attribution method that quantifies the interactive contribution between two elements, say, a word token and a joint token, across varying contexts. Unlike standard Shapley values, which measure individual contributions, STI, at order k equals 2, captures pairwise interactions. It asks, how much extra value does this pair add when they appear together, compared to when they appear alone? To compute this, we consider all possible permutations of tokens in a batch. For each pair, we measure the marginal gain in retrieval score, when both are added to a growing prefix subset. The expectation over all permutations yields the STI value. Higher STI values indicate stronger semantic alignment. But computing STI exactly is computationally prohibitive. So we introduce a lightweight STI Estimation Head, a small network with convolution and self-attention layers, that learns to approximate STI via Monte Carlo sampling. This head outputs probability distributions over motion-to-text and text-to-motion alignments, which we then train using a KL divergence distillation loss. The result? A model that mimics the fine-grained interaction modeling of STI, but efficiently at scale. Now, how do we integrate this into the pyramidal structure? We use a token compression mechanism to move from fine to coarse. At the joint-wise stage, we have fine-grained tokens for every joint across time. Then, we compress these into segment-level tokens using a KNN-DPC clustering algorithm, which selects cluster centers based on local density and relative distance, preserving the provenance of original joint tokens. This compression is not just about reducing dimensionality, it's about semantic aggregation. Each compressed segment token inherits the meaningful structure of its constituent joints, enabling coherent segment-level alignment. At the segment-wise stage, we compute STI between phrase-level tokens and motion segment tokens. Then, in the final holistic alignment stage, we aggregate all segment tokens into global representations, text and motion, where we measure overall correspondence via contrastive learning. The full training objective combines three components. 1. Contrastive loss at each stage, joint-wise, segment-wise, and holistic, using InfoNCE to pull matched pairs together and push negatives apart. 2. STI distillation loss, to preserve fine-grained interaction signals learned at the joint level. 3. Self-distillation loss, to align similarity distributions across stages, preventing misalignment between levels. Together, these components ensure the model learns consistent, hierarchical correspondences. We evaluate our framework on two major benchmarks, Human ML 3D and KitML. Under both the all and small batch protocols, our method achieves state-of-the-art performance. On Human ML 3D, we surpass all prior methods, improving R at 1 from 12.45 to 13.83 with LLM-enhanced text, and reducing median rank from 10 to 7. On KitML, we achieve 16.01 R at 1 and 7 MEDR, setting new standards. But numbers only tell part of the story. Our visualization analyses reveal the true power of PST. At the joint-wise level, we see dark, localized color intensities, highlighting strong semantic matches between specific joints and words. For example, arm swings aligns precisely with the trajectory of the left arm joint. At the segment-wise level, we observe coherent groupings. Walk forward maps to a synchronized sequence of limb and root movements, while stop corresponds to a deceleration and stabilization of all joints. These visualizations aren't just pretty, They're evidence of interpretability. The model doesn't just retrieve the right motion, it knows why. We also conduct ablation studies. Removing the STI distillation loss drops performance by over 2 points in R at 1. Eliminating the self-distillation loss causes misalignment between stages. And adjusting the compression ratio, too low or too high, degrades results, confirming the importance of balanced aggregation. One limitation remains: the model struggles with rare or complex motions. Why? Because the training data is dominated by common actions. To address this, we explore LLM-driven text enhancement. By using QN2, 5-7b instruct to decompose holistic descriptions into part-level, fine-grained annotations, we enrich the training signal. When retrained on this enhanced data, our PST++ variant, we see further gains, especially in small-batch evaluation, where robustness is critical. This suggests a promising future. Fine-grained retrieval isn't just about better models, it's about better data. By aligning text and motion at the same structural level, we close the semantic gap more effectively. In conclusion, PST learning redefines motion-language retrieval. By mimicking the human perceptual hierarchy, embedding Shapley-Taylor interaction for fine-grained alignment, and enforcing consistency across scales, we move beyond global alignment toward true, interpretable, and precise cross-modal understanding. This is not just a technical advance. It's a step toward machines that don't just see motion, but understand it one joint, one phrase, one interaction at a time. And that ultimately is the future of human-centered AI.